Okay, I'd like to welcome everybody here today. I'm Andrea Copping with Pacific Northwest National Laboratory and representing Ocean Energy Systems Environmental. And you can see that we have quite a group working with us here today. Lisel Garavelli and Linnea Hemry from PNNL, from Aquaterra, Jen Fox and Rayanne Miller, and Andy Seitz from the University of Alaska Fairbanks is going to be our featured speaker here today. This is the workshop on collision risk, specifically about fish and turbines. And the intent is to talk about understanding and how we might get towards retiring this risk for consenting or permitting. Okay, go ahead, Debbie, to slide 3. Thank you. So today we have 3 hours. We are going to talk about some introduction to collision risk and encounter risk models, because that's very much where we're going to try to go to today, is what data do we have and what do we need to drive models. We will have Andy Seitz' presentation on fish and turbines, do a quick introduction of what we're going to do with breakout groups. Then we will have a breakout group. You'll be divided automatically by Debbie into your specific rooms, which is why having your full name is really helpful. And that'll all happen automatically. And that will really focus on how we have used models and data so far. There will be a quick break after we do a report out. And then a quick presentation on how models have been used in a case study. A second breakout group will then take place. Again, you'll be put into those breakout groups, and we'll discuss how the models are doing and how we can improve upon them. There'll be a report out and then an open discussion. So we have a lot to get through in the next 3 hours. So we'll just go ahead there. Next slide, please. Just a quick note that this workshop is put on by OES Environmental and ORGEP. OES Environmental, if you don't know, is under Ocean Energy Systems, which was established by the International Energy Agency. I believe there's 25 nations plus the EU are members. This particular task is focused on environmental effects of marine renewables, wave, tidal, etc. And there are 16 nations participating in this particular initiative. It is led by my organization, Pacific Northwest National Laboratory out of the US. And yes, we did just have another country join. And we use the Tethys platform, I'm sure many of you are familiar with, to coordinate and record these activities. Our latest output, if you will, was the 2020 State of the Science report that came out in September. So I'll pass this on to Jen for ORGEP.
Thanks, Andrea. So ORGEP Ocean Energy, hopefully many of you know of the program. If you don't, I'll just give a very brief introduction to what ORGEP is. It's a UK funded program and has very well aligned aims and objectives as the OES environmental program that Andrea was just introducing. So the aim of ORGEP overall is to reduce the consenting risks for wave, tidal stream and tidal range projects. And it does that by facilitating a strategic, coordinated and prioritized approach to monitoring and research around those wave and tidal energy projects, which is endorsed by industry, regulators and statutory nature conservation bodies. So much in a similar way to what Andrew was saying, you know, this kind of facilitating the prioritization and the strategic discussions around the key evidence gaps or knowledge gaps in relation to environmental impacts of the wave and tidal energy industry. Some of the key outputs I've just put on the slide here are the forward look document and also a report we produced last year called the Critical Evidence Gaps of Wave and Tidal Energy. Those are both available on the ORGEP Ocean Energy website. And if you're interested in hearing more, we have a really great network that we engage with on a regular basis. So you can become involved in our network by just sending us a quick email to orgep@aquaterra.co.uk. I'll pass over to you, Andrea.
Thanks, Jen. Okay, the goals of the workshop. What are we trying to do today? We're trying to look at how models can help us understand collision risk and turbines and how This will directly help consenting or permitting. We're going to look at knowledge and data gaps that limit our understanding of collision risk. We're going to look at methods for collecting the necessary data. I want to warn you now, we're not talking about instrumentation per se. We had a workshop almost 2 years ago now looking at this when we were in Edinburgh, but rather what are the kinds of data we need to collect. We need to think of how suitable the models are for assessing collision risk, but also population effects. And we need to identify those data that are needed to parameterize and validate the models. And you are all here today because of your interest and your expertise. And we really hope we can leverage this interest and expertise to really work towards some international collaborations, identify those particular data collection needs, maybe even research projects among them, and get some international collaboration. We're starting to get some traction actually with several countries being willing, the funding agencies willing to put money towards a collaborative project. So that's something we're really interested in here. Okay, at this point, I'd like to hand it over to Lisel Garavelli on the next slide, who is going to talk about the existing models, what they mean. Think of this as sort of an introduction or a primer to collision risk models. Go ahead, Lisel.
Thanks, Andrea. Hi, everyone. We just wanted to put everyone on the same page about a collision risk model. So next slide, please, Debbie. Sorry, it's early. Here we go. So we wanted to start with some definition of, I'm going to talk about several terms here. So just wanted to put everyone on the same page with some definitions. First of all, in models, we can have several behaviors such as the avoidance, which occurs when an animal is responding to and moving away from a device at great distances. We can have also the evasion, which is when an animal is changing its behavior to escape a contact with a device at close distance. So that would be after the encounter, but averting the collision. Next. I'm going to also talk about other terms here that I wanted to define. So first of all, the encounter, which is an animal being in the near field of a turbine between 1 and 5 devices length. The collision of an animal, which is when an animal is being in contact with the blade of a turbine. And I will also mention exposure time, which is the amount of time an animal spends at the depth and in the field of a device. So what do we use collision risk models for? The purpose of collision risk model is first to estimate the likelihood of an encounter between an animal and a device, and second, to estimate the likelihood of contact, which is the collision, between an animal and a device. The rates of this encounter and collision depend on the size of the location of the device, the animal behavior, the animal ability to detect the device, and the animal behavior in response to the device. There are different outcomes to collision risk model. The first are the probability of encounter or collision, but if we have some idea of will the animal survive after the collision, we can actually look into some effect on the population. Next slide. So I'm going to talk about 3 different types of model today. The first 2 are to estimate the interaction between animals and devices. So the first model I will mention is the encounter rate model, which estimates the likelihood of being in the near field of a turbine. The collision risk model, which estimates the probability of contact between an animal and a turbine. And the last model I will mention is to estimate the potential effect of a collision to the population. This is called the exposure time population model, and it associates collision risk to population effects by estimating the rates of fatal collision that leads to a specified detrimental effect on the population. Next. So first, the encounter rate model. This is a predator-prey model that integrates the volume of water swept by a predator. Here, the predator is the blade of a turbine. This model integrates the size of the prey density, and the relative swimming speeds of predator and prey, so swimming speed of the blade and the animal. I mean, not swimming for the blade, but the speed of rotation. So in this model, the turbine blade is viewed from the side, and it sweeps a certain volume of water in a unit of time that an animal has some probability of occupying. And it estimates the likelihood of encounter between prey and predator, and it's also best suited for horizontal axis turbine. Next. So the next model I wanted to mention here is called actually collision risk model. And there are two types of collision risk model. The first one is a numerical model, which is based on Bain study and was developed for birds and offshore wind farm. This model integrates the area covered by the rotor, the size of the animal's transit time across the plane of the rotor, and the animal's behavior and density. This type of model is used to estimate the probability of collision between an animal and a turbine. It is also sensitive to assumption about avoidance rate, and it's best suited for horizontal axis turbine. There are really few models that include actually the avoidance or evasion behavior. And in some studies, this behavior is based on behavioral observation of fish. So this is an Amar et al. Study. Or there is also some behavior based on the injury risk that is based on the part of the animal's body that contacts the rotor. So this is a Koping-Ingrier study. Next. For collision risk models, there is also what we call a spatial stimulation. And this is used to represent the animal and a device over time in 3 dimensions. This type of model integrates the shape and movement of a device, the animal's behavior, and the animal's size. And it is used to estimate the probability of collision between an animal and a device. The variation in input parameter here influence the collision probability, such as, for example, the vertical migration of fish in the water column. And this type of model is used to integrate can be used to integrate the relative complexity of a tidal kite compared to other models which were more used for tidal turbine. And they can also they can also include the interaction with flow. Next. Finally, the last model, the exposure time population model. It's the model that was developed for diving birds, again, by Grant et al. In 2014. It approaches the collision risk here from the perspective of the population. And this model integrates 2 models, a population model to estimate the amount of additional mortality caused by collision that will not decrease the population growth rate, and an exposure time model to estimate the collision probability from the amount of time the animal spends at the depth of the device and the proportion of that depth occupied by the device. So this model is used to estimate the collision risk per unit of time based on the population size and individual exposure time. And it also provides a threshold mortality rate. So important to note here, this model assumes that every collision is fatal and does not include avoidance or evasion behavior. Next. So overall, the inputs required in this type of model for fish to look at the collision risk are the population density, swimming speed, the body size of the fish, length and width, behavior, which can, for example, vertical migration. And in the case of the exposure time population model, the inputs required are the reproduction and survival of the population. And next slide, this is my final slide just to conclude on collision risk model. As I say, they are used to estimate probability of encounter and collision, or to estimate or they have a mortality threshold that would affect a population. In this model, the behavior can have large effects on the outcome, which create uncertainties when using behavior with limited information. The injury outcomes, death, and population effect are usually not considered in this type of model. And the outputs are mainly predicted for one single turbine in most of the studies. And there is actually one study looking at fish strike probability for arrays, but there's not a lot of study about this. So finally, the empirical parameterization of behavior and densities in models is rare, and there is no existing validation of predicted collision probabilities. Thank you very much.
Hey, everybody. So my section is helping develop collision risk models for fishes, and an alternative title, if you want to bump forward, is Collision Risk for Fishes: What is known, what is not known, and how do we collect it? And this is aimed at gathering information that can inform future modeling efforts. Next slide. And I'm giving away my punchline here a bit, but the research is really in its infancy, and there's not much known about fish behavior around turbines compared to more mature fields, and it's because it's a relatively new field, and it's resulted in largely non-transferable results. So there have been studies around the world done on this, but they've used different approaches, they've studied different fishes, and they've been conducted in different environmental characteristics. And so it presents a lot of challenges, which also makes it an exciting field. So next slide. And so my summary will go over what's known, what's not known, and how do we get that information. And to gather what's known, I searched through the TETHIS database. And then this is also based on some personal experience. And so I've been conducting research in the Tanana River for almost a decade now. And here's a picture of us collecting baseline information about which fish travel in the river margins versus the middle of the river where turbines will get placed, which can inform things like encounter probabilities. So next slide. And some of the general results that I'll talk about today come from a variety of places. I've added stars to this nice global map here. Where field studies have taken place, these stars don't indicate where flume or laboratory studies have taken place. And I may have missed studies as well. And so if I've missed something here, if there's a missing star here, please feel free to let me know at the end so I'm up to date on what's going on. Next slide. And the studies that have been done on in both the wild and in laboratories have been done on a variety of species. The point in showing this huge list is not to have you read through every scientific name here, but just to demonstrate that there's been a variety of species examined. You can go to the next slide. And then here's a second slide. All of these species were examined off the island of Madagascar, and so we have a nice variety of both temperate and tropical and subtropical fishes on which research has been done. Next slide. And then the research has been done looking at fish behavior around a variety of turbine types. Again, this is not exhaustive, but the purpose is to show you that there's no standardized research approach on a standard turbine design. And so there's been horizontal axis and vertical axis and different engineering designs of turbines that have different characteristic environmental fields around them. Next slide. And then they've used a variety of monitoring approaches, including in the upper left, Didson or ARIS cameras, acoustic cameras. Some studies have relied on optical cameras, such as in the upper right, and then other studies have relied on more traditional echo sounders, such as in the bottom there. And each approach has different strengths and weaknesses involved, and they lead to different confidence and conclusions. Next slide. And so now I'll focus on what's known, and I'll break it down into different stages of what's known. But this gets, the first part that I'll talk about is baseline information and then distribution information around turbines. And these are admittedly really general, and that's on purpose because a lot of the results have been fairly general. And then a lot of the results have differed between studies. And so it's hard to make broad sweeping conclusions based on multiple studies, because a lot of the studies have different findings. But in general, fish seem to shoal around turbines, such as that seen in this picture here below. So there may be an attraction effect of turbines, and this may be used fish-like structure, and so these turbines may be used for protection and feeding. But this attraction effect and an abundance around turbines seems to be inversely related to tidal velocity. And so a lot of this research was done in tidal areas. And so when the tidal velocity is slow and the turbine is not moving as quickly, then there seems to be more of an attraction effect, leading to greater abundance of fishes around the turbines. And then vice versa, when the turbine is moving quickly, the fishes seem to stay farther away from the turbine. Next slide. And then when fish are actually around turbines, this is the behavior aspect, or the findings of fish behavior around turbines. But fish are not, and this shouldn't come as a surprise to anybody, but fish are not just passive objects moving through an environment, but they actually make behavioral decisions. And when fish do encounter a turbine, they frequently avoid the turbine. And this is valuable information for modeling efforts. And it seems as though there's fewer interactions when the turbine is spinning. And I'll visit, that's probably, there's an avoidance effect, or a reaction to some sort of field coming out of the turbine. And I'll talk about that in a bit. It seems schools of fishes react farther away than individuals do to a spinning turbine. And there's collective knowledge in a school that gets transmitted through the school versus compared to an individual fish. There has not been a lot of study on passage delay for migrating fishes, but of the limited studies that there are, there's no evidence for passage delay of migrators, which is a big question for environmental regulators looking at indirect effects of turbines. So even if there's not a collision, will turbines cause a passage delay in migrating fishes trying to get from location A to location B? And then there's been some limited research on day versus night effects. And of that limited research, it seems that turbine entry is higher during the night. And this may be related to visual cues, fish that rely on primarily vision. And so the figure on the right is a figure that Sherry Matzner made examining behavior around the ORPC RivGen turbine in the Kwijak River. And it just breaks down different behavioral types based on information gathered through optical cameras. And you can see that some fish avoid above and below and reverse and around and pause and through. And so there's a variety of different behaviors that fish can undertake when presented with a turbine. Next slide. And then the next stage of this, so we've moved through baseline information and distribution information. We've looked at behavior around a turbine, and then in some cases fish actually pass through turbines. And there hasn't been a lot of information gathered about fish passing through turbines in the wild. There was a study in the Hastings in Minnesota with fish forced through a turbine and then collected further downstream with balloon tags. But most of this information about outcomes of passing through a turbine comes from flume studies, where fish are actually forced through a scaled down turbine. And it seems there doesn't seem to be a lot of obvious injuries for fish passing through turbines. But of the fish that do show signs of injuries, the harm and mortality depends on the species. Seems to be some species are more susceptible to injuries than others. Age of the fish, which is related to size of the fish. Smaller fish seem to get pushed out of the way more easily by a spinning blade. The entry angle, so if they're struck by a blade, the angle of the blade strike is related to the outcome of the encounter. And then turbine characteristics, so how quickly they spin, how blunt the leading edge of the turbine foil is. Next slide. So what needs to be known? This is To me, probably one of the more important slides, because there really isn't a lot known and we have a lot to learn to better inform modeling efforts. And so I've broken this down into two categories of broader research that would apply across different sites, and then project and location and species specific that needs to be known for research efforts at different sites. And so the broader research involves understanding near field events, and these are understanding encounter and behavior around turbines and this was taken from the literature at less than 10 meters. And we don't have a clear, we have a better idea of what happens at farther distances, such as 100 or 50 meters, than we do when fish get very close to turbines. And a lot of that's because we don't have a lot of high resolution data, such as optical cameras of behavior in the near field of the turbine. Related to near field events is identifying collision versus near miss. And so for fish that actually enter a turbine, and the turbine is spinning, does the blade actually push the fish out of the way, or does it actually strike the fish? And so we don't have a good idea about whether fish that enter turbines have a near miss or whether they're actually getting struck by blades. And again, this is related to lack of high resolution imagery when fish are within a turbine. There's nighttime events and light questions. So specifically, turbine monitoring needs to occur at night as well, because some fish move more at night or move less at night. And so it's important to study both daytime and nighttime. And but to study fish at night using optical systems, we need lights. And so we don't know if the lights serve as an attractant or a repellent. And so there's a need to understand how our monitoring approaches actually affect diel behaviors. And then on a very broad scale, we need to think about monitoring approaches and systems. There's been a variety of different systems used, and it would help increase the transferability of results if some of the systems were more standardized, if that's possible. I realize that in some places and times that's not possible, but some sort of standardization or recognition of how different systems relate to each other would be helpful for understanding modeling efforts. And then automated analyses. A lot of the analyses rely on plug and chug or visual analysis of different streams of data collected by monitoring equipment, and automated analyses would make that much less time intensive. And then for project location and species specific information needs, there's a need to understand effects on mass migration of fishes. So a lot of the research so far is focused on individual fishes at individual levels, not schools of fish. There's a need for information for direct blade strike effects. So do fish survive a blade strike, or do they make it out okay? The condition of fish passing through a turbine. So are there pressure related issues of passing through turbines? It's likely that there's not, because the pressure field of turbines is relatively low compared to traditional hydropower. And then something that has never been looked at in an in situ situation is multiple deployments. All the research has been done on single turbines and fish behavior around those. And so if fish encounter a turbine array, we need to determine what happens or how fish behave around multiple deployments. And then this relates to the next point, which is cumulative impacts. And so are there cumulative impacts to fish that encounter multiple deployments in an environment? And then perhaps most importantly is relationships between turbine characteristics and fish behavior. There hasn't been a lot of research on understanding the environmental fields produced by a turbine, such as noise, particle velocity, turbulence, things like that around a turbine, and how fish behavior correlates to those environmental fields around a turbine. And that gets to the crux of how do we predict and model fish encounter probabilities and collision risk. Next slide. And so how do we collect this information? Like I said, it would be good to develop more standardized approaches, or at least best practices in given situations, and apply these to field studies at 3 different levels. So baseline information such as fish presence and absence in an area where a turbine is planned for deployment, interactions, so how do fish behave around a turbine and in relation to environmental fields, and then the outcomes of fish encounters with turbines, and if they pass through a turbine, what are the outcomes of those? And then I boldface this because I feel strongly about this, but modeling will be dependent on determining the root understanding of species-specific behavior. So determining how does fish behavior relate to the different environmental fields around a turbine, and that will inform the modeling efforts of understanding fish behavior and collision risk. And then I've used this picture. I'll just wrap up real quickly. I've used this picture. This was on the title slide, and I have it on the closing slide too, to demonstrate the challenge that we faced when doing this. This is a turbine foil on the RivGen turbine when we were trying to determine how well does our optical camera system work. And this is a fishing lure in the just to the right of the turbine foil there, and then there's a little stickleback about a foot to the left of the turbine foil. Yeah, so that's the fishing lure, good eye, and then the stickleback is up here. And so these are the challenges we face. These are not easy to see, and then how do we detect them and then quantify them? And so we've got quite a challenge ahead of us.
We had a very great lively group. We will talk till the very last second and beyond. We had a mix of Scottish, Welsh, US, and European participants, regulators, advisors, and researchers. We got down to the very nitty-gritty about knowledge gaps and how to solve them. And the big ones that really came forward, we recognized we need to know everything about fish and turbines, but being able to get a sense of which fish are likely to be swept aside from turbines versus those that are heavy enough that they might be carried through, and some thoughts about how we might achieve that. We thought about how fish react to different cues from the turbine. Do we understand enough about some of the fields around turbines, the sound, the pressure, the turbulence, particle motion of sound, etc.? And if we knew more about that, we might have a better sense of how fish would be reacting to those fields as they approach a turbine, and therefore what their behavior is likely to be. Let's see. So we thought that being able to really, it came down to getting probably a little closer to some of the engineers working in these fields, looking at fluid dynamics and hydrodynamic modeling of how animals might behave, and especially the smaller fish might be affected by the hydrodynamics around a turbine. And also, what are the cues coming off the turbines that are being worked on by the engineers, but very separately from the fish work. Then as far as how to go about collecting these extra pieces, the recognition was that so often fish studies are just an add-on at the end of a project, of a deployment going in the water, and that a little bit of progress is made, at least enough for the developer to be able to get a consenting or a licensing, but that those studies then end abruptly. And what we really need are dedicated studies on fish and turbines, so that we can really understand from sort of start to finish what's going on. And those studies need to be longer term than just a few weeks or a month because of the seasonality differences. We recognize that density studies of fish are really important, but they're difficult to do, and that probably the real solution to all this is the need to have integrated instruments, active acoustics, cameras, etc. And then we got off on quite a discussion about underwater cameras, the value of being able to use them, but they are not always feasible in different environmental conditions, turbulence, turbidity, and so on. But then towards the end, we got to the point where there's some interesting things being done in the fisheries side, fisheries management side, from studies on bycatch, particularly trying to use different wavelengths of light that for which fish such as salmon may not be sensitive. We also acknowledge that the need to be able to automatically process underwater stills and video in order to really get to the kinds of answers we need. And that's about where we got whisked back to the room. So that's it. My group, anything I really missed there?
No, I think you captured that really well. Thanks.
Thank you, Rebecca. Okay.
Shall I go next?
Yep, you're up, Jen.
Okay, so my group, a lot of similar points to what you were saying, Andrea. I'll just pick out a few key things in brief that we covered. So we focused in quite a bit on the need for really great baseline understanding of things like fish behavior, fish density, presence and absence of migratory routes, and those types of things. And we kind of came to a point where we acknowledged that maybe we do know more than we think. So there's an element there of just improving our general knowledge transfer and accessibility of data and knowledge and those kinds of things, but definitely an acknowledgement of the need for greater understanding and greater baseline studies and for that information to be available. That was the kind of key thing that we focused in on as being the key pathway through to being better at this stuff and being able to streamline the consenting process. We did also focus on things like the energy payoff and the reasons why fish might be in certain areas, and having a good understanding of that will help with that general baseline understanding and understanding of behavior. We talked a bit about where we're looking to get to, so what's the end point and what's the kind of ideal situation, and there was some agreement that the ideal situation is that we would have fantastic maps of key sites for tidal energy developments, where we would know about fish abundance and fish behavior and migratory routes and those and all those types of things, and you would be able to drop your tidal development in there and be able to very quickly and in a very streamlined way have an understanding of what the potential impacts might be based on that kind of baseline information. And then we did talk a bit about, if that's the optimum situation, let's be realistic and talk about what's reasonable or what's likely. And there was some acknowledgement that in the beginning there isn't going to be a huge amount of data transferability because there's so much site to site variability, or also potentially species to species variability. So there will be a need for this high amounts of baseline data collection in the beginning so that we can categorize and increase our abilities to transfer data between sites. And so that's where we want to get to, but an acknowledgement that we're quite far from that. And so there's a lot to do to be better at that baseline understanding of fish presence and fish behavior. And there was another point that we wanted to get to, which was, the key part of being able to get to that endpoint is, as Andy was already talking about this morning, the standardization of methods and data collection efforts is going to be a really important part of being able to get to that endpoint. Was there anything from my group that I missed out? Any other key points that you wanted to highlight? Anyone? No. Okay, I think that was it from us.
Great, Lisa, you're up.
Yes, thanks. So for us, that we had it's a lot of similar points as Andrea and Jen. So this is good actually for us at the end. But we talk about for knowledge and data gaps, the need to specify generalized data versus specific data. And that will, we talk about also you mentioned already some, how does the hydrodynamic around blades affect the behavior of the fish? And the fish presence also need some data about fish presence, fish school in relation to tidal phase. For the population model, a need to know evasion range as a function of distance for any species of interest. And also again, so this fish abundance and evasion behavior was actually the main key missing piece that was highlighted. So if we look at generalized data versus species-specific data, we talk about how, if we had them, what would it mean? And that would mean that we would have less data collection required for those generalized inputs, which would be good. The hydrodynamics, we mentioned that if the turbulence pushes fish away from blades, the potential for fish mortality will be reduced. So it would be good to know what are the hydrodynamics around. Also knowing what kind of fish, the species, if the fish are small, also occur at a site, and if they can control their vertical distribution in the water, in turbulent flow to evade or avoid the turbine. This will definitely help with model validation, model parameterization, and that will also help having more support from stakeholders in terms of tidal energy project in areas where there are important commercial fisheries. And the endpoints, we mentioned some standardized tool for assessing the risk that would be really helpful. And after, when we talk about some data collection, so again, need to have specific data at each site to understand how fish will interact at one location. Video or data are very useful, but this again would depend on the site, and the limitation was brought with the visibility and also at night. So one thing we talk about is like, if we know the species during the day that is present, that would help us set up technology to monitor during the night. So what Andrea mentioned earlier about salmon, knowing like which wavelengths the fish would be okay with. And a big point that was brought was that the data acquisition should be connected to specific objective, and the species variability is valid, but we need to know the objective to understand what is missing, and sensitivity analysis could actually help with that. And in my group, let me know if I missed something. Thank you.
Thanks, Lisa. Rayanne, you're up.
Okay, thanks, Andrea. I think I'll just keep it brief because a lot of similar points have been said in each of the three previous groups, but perhaps an important point that sort of came out from our group was starting with the worst case scenario and actually trying to understand, do fish actually collide, which really is the crux of this entire workshop of everything. And you know, just we talked quite a bit about what happens up close, and actually how do those flume experiments with very small fish translate up to very big turbines, very different flow speeds and very different sizes of fish. So you know, there's an element of understanding fish behavior in the near field or very, very close to turbines, but yeah, essentially understanding, you know, the crux of that question: do fish actually collide with turbines? One of the reasons that that's quite important is for verification of models as well. So being able to actually understand how good the models are. Another thing that we discussed a bit was sensitivity analyses, and sort of trying to understand what matters most. And I think that's been mentioned already, but focusing data collection on the things that do matter most, and just taking that all the way through to what that would mean. You know, going from, I think somebody gave the example of 3 data points to 25 data points can actually mean a huge amount to a regulator in terms of consenting a development, and that really can give regulators more confidence. And just one final point, we kind of talked a little bit about the challenge of recording very, very rare events, i.e. an actual collision or fish behavior in the vicinity very close to a device, versus using something like modeling, which can predict very, very rare events, and where the line kind of gets drawn between actually observing those events and using models to predict them. Happy for anyone else to add in if I've forgotten anything.
Great. Thanks, Ryan. Linnea, you're up.
Yeah, so like the previous groups, we covered a lot of the same aspects. But in our group, for the first questions, in addition to missing baseline data for different sites on behavior of fish, we also talked about knowing more about the devices themselves, the turbines. We do know there are different types of turbine, but how do they interact with fish? What's the difference between different types of turbines? Then how do we get into solving these gaps? We talked about the great need of having, of measuring, collecting data throughout the year, and not just during summer when the conditions are better, but throughout days, day or night, on winter, summer, all the different aspects, because the fish are there year round sometimes. We talked about also having comparable data sets on standardized data, metadata, some guidelines for collecting this data. And also something I didn't hear before, we talked about the importance of educating regulators, but also stakeholders, fishermen, and the general public about what is the risk of fish colliding, that it is not decimating fish population. And so there is need for better disseminating the information on. Andrea, I see you smiling. Yes, we are trying to do that. So that was brought in the group. What is the endpoint? There was a few different interesting endpoints in our group. One that's familiar to probably a lot of you now is retiring the risk of collision risk with fish. So we are not there yet, and we are slowly inching our way, but there is still so much more to do, and that's why we are doing this kind of workshops. We also had an endpoint having a better communication between turbine designers and fish biologists on identifying all the little parts of a turbine that could be harmful to a fish, on having more standardized like gaps underneath the turbine for fish to slide through under, or things like that, because devices are very different from each other. And how to collect the data. So one of the big discussion we had was around guidelines on not standardization, but guidelines on recommendations for how to measure. Like, if people want to use video, that's great, but let's make sure that they use it in the proper way, that the data at the end, the footage that you record, are actually useful. If we want to do machine learning or artificial intelligence for processing the video afterward, video needs to be of good quality and actually record useful data. So we need guidelines for fish biologists to know how to use a video camera properly. And we also had a discussion about keeping in mind the environmental difference between the sites, and then combining video and sonar acoustic data so that all different seasons and visibility differences can be covered. Then I think there was also a point about improving stock assessments to the fish stock assessment to the right scale. Stock assessments are often done at an ocean basin or country scale, and might need to be done at a smaller scale, the scale of a tidal site.
Great, thank you. So Catherine, last one.
Yeah, so a lot of similar threads coming through into the discussions. Our group started looking at the data gaps, and a lot of the discussion was around in terms of how the physical environment and the hydrology around a deployment affects the biology and the behaviour of the species under investigation. And the research priority being the behaviours of the fish in understanding collision risks. Looking into things like the migratory fish routes and the abundance, as well as reactions to the device itself in terms of at night time and with artificial lighting. Are they attracted? Is that going to be something that we need to think about a bit more? In terms of looking at the endpoints, we're hoping that this brings better understanding of our species-specific risks and understanding turbine-specific effects. And as I think Jen had said earlier, we're still a wee bit away from data transferability between sites. I think there's a few nuances that we need to learn at each site first. We had a good comment about needing to be able to operate in terms of deploy and monitor to actually gather the data that we need to validate our model predictions and adjust expectations accordingly. And following on from what a lot of people have said already in terms of we need to look into how we standardize approach, and for the difficulties that come with monitoring fish in these kind of challenging visual environments, we need to look into combining a variety of approaches and technologies to be able to capture their behaviors and better understand them. And last point, just checking the screen, was making it bigger. So yeah, we need to look into how we collaborate between sites and make sure that we can produce data that is comparable based on the methodology. So there's an agreement to the approach in designing your monitoring systems for understanding collision risk. And I think that was most points, and again I'll open it to the group if there's anything else that you'd want to mention. Otherwise that's our group so far.
Terrific. Okay, thanks so much. We are capturing these Jamboards, of course, and we'll have all this pulled together in a report at the end. So next we will have a presentation by Rayanne Miller, which is going to really just give a little bit of a flavor of how risk modeling collision risk modeling has been used in practice with fish. And this was really just to set the stage a little bit for our next breakout group, thinking about how the models are used. So it's all yours, Rayanne.
Thanks, Andrea. And I'm drinking a cup of tea here in Scotland. So yes, my name is Rayanne Miller and I'm a senior consultant at Aquaterra. And those of you that know me will know that I'm not a fish ecologist, nor am I a modeler. However, my job here is to present a bit of information that hopefully we can use to spark the discussion going into the next breakout session. So can I have the next slide, please? So I'm going to focus on some of the activity that's happened around the MAGEN development, and I'll just give a brief overview here for those. I know we've got quite an international audience here. So the MAGEN development is sited in the Pentland Firth along the north coast of Scotland, and they completed an EIA in 2014, and that resulted in a marine license being granted to the site. Construction commenced, and in 2018, the first phase of the MAGEN development officially went into operation. So this phase is comprised of 4 tidal turbines, 3 of which are Atlantis Resources turbines, and 1 is an Andritz Hydro Hammerfest turbine. So there's two different types of turbines, but both of them are horizontal axis turbines, and they have 3 blades. So the consent for this development was sought in phases. So initially there was the initial phase was seeking consent for 86 megawatts, so up to 86 turbines, and the next phase is going to be sought separately, and that'll be for up to 312 megawatts. And just to say that each one of these tidal turbines has an export cable to shore. So next slide, please. So what I wanted to do over the next few slides is really look at the progression of collision risk modeling from the initial modeling that was done in the Maygen environmental statement, and then look at how that was then reviewed by Marine Scotland in 2013, and then again how that was progressed as part of Scottish Natural Heritage's 2016 guidance. So really what I want to show is how different inputs to the models, or slight tweaking of the models, resulted in different types of outputs, just again to give a bit of food for thought for the next bit of discussion. So next slide, please. So just a quick note to talk about Atlantic salmon in the Pentland Firth. So in the Maygen environmental statement, the collision risk modelling was carried out on Atlantic salmon for a couple of different reasons. First of all, there was no specific fish ecology survey done in the Maygen environmental work. However, in the case of salmon, there's the most data was available of the majority of fish species for Atlantic salmon. And also, given that the entire regional population of Atlantic salmon migrates through the Pentland Firth, so about 90% of all Scottish salmon return to the east coast. And what you see in the picture here, the red arrow indicates where the Pentland Firth is. And in the purple lines, you see kind of squiggling across Scotland. Those are all special areas of conservation for Atlantic salmon. So again, 90% of salmon returning to the east coast of Scotland do so through the Pentland Firth. Return to the Pentland Firth, and 88% of that 90% do so via the Pentland Firth. So essentially Atlantic salmon was considered a worst case scenario for fish collision risk. Next slide, please. So again, just a little bit of background. So the most comprehensive data was available for salmon in comparison with other species of fish, which were present in the Pentland Firth. And in the initial work, in the environmental statement for Maygen, they estimated the probability that a smolt, a grilse, which is a first-year salmon, or a multi-sea winter salmon, so you'll see the acronym MSW, encountering turbines as part of the different sizes of array. Their input parameters were the frontal area of the turbine and array, the depth distribution of fish, and you'll see that that's one of the characteristics that varies as the modelling progressed. The proportion of the population passing through the array space, and the proportion of fish surviving passing through the turbines. And then, so that produced an encounter rate, and various avoidance rates were applied to those encounter rates. It's worth noting that when I talk about the Marine Scotland, or MSS, Scottish Natural Heritage Review that was carried out, they deemed that the risk to smolts was very, very low, mainly because of the small size of the smolts, but also because there was no strong indication that Scottish smolts migrated through the Pentland Firth. So that's not included in that study. Next slide, please. Sorry, yeah, thank you. So what I'm going to do in the next couple of slides is just, I've picked out a few of the different parameters and I've put them into tables. I'm not going to talk through all of the tables because I think everyone would be bored to tears. But what I do want to point out is just where some of the differences lie. So a key one here, a key difference between the Maygen study, the Marine Scotland SNH study, and then the SNH guidance note, is the distribution, particularly the vertical distribution of salmon that was used in each one of the studies. So at the time of writing in the Maygen report, there wasn't very much information, or much information with great certainty about adult salmon distributions. So in that environmental statement, they assumed that salmon was distributed uniformly across the Pentland Firth, both across the width and the depth. And as such, given the height that the turbines were operating at, or the water depth the turbines were operating at, they assumed that 57% of adults passing through the Pentland Firth would do so at turbine depth. Now, this was then updated in the Marine Scotland SNH review of that in 2013, where they used adult vertical distributions based on tagging data. And actually, using that information, it was deemed less likely that adults would swim at turbine depth. And so therefore they calculated that only 16.6% of adults would be at turbine depth. And again, more information was added in the 2016 version, so the SNH version. And that was following a new study by Godfrey et al. In 2015, which provided even better granularity in terms of salmon vertical distribution. And actually in the, so that study contains a worked example at the end of it. I'd recommend going and having a look at that report if you haven't already. But the percentage of salmon within the turbine risk depth was actually only 10.6% with that updated data. So it's just to illustrate how that vertical distribution data can really make a difference to what goes into your collision risk model. Next slide, please. So just another one to highlight here, in the Maygen environmental statement, in terms of the cross-sectional area of the turbine array, to do the modeling for 86 turbines, they used one row of 11 turbines, which was calculated to occupy about 1% of the Pentland Firth, and then added another row of turbines behind that, which was offset from the first row. So using those first two rows as essentially the frontal area of the entire array gave a cross-sectional proportion of about 2% of the Pentland Firth. Now, the review of that by Marine Scotland and SNH suggested that that was inappropriate, and actually what they needed to do was multiply the rotational plane of a single turbine by the number of turbines. And so for 86 turbines, that actually gives 8% of the Pentland Firth as cross-sectional area. So again, you see that's another, these kind of subtle interpretations, again, could give different input parameters to the collision risk models and therefore different outputs. And just to say again, in the bottom row there, the turbine operation rate differed between these studies as well. And again, that's coming with data refinements as the array's been in the water for longer. Next slide, please. So I didn't have too much to say here, but what I did want to just illustrate again is that regardless, particularly between the Maygen and the Marine Scotland review, the collision rate, or I suppose the assumption of how many adult salmon would collide with a turbine as it passes through that space is approximately the same. There was a little bit of updating the SNH report in 2016, so you see that approximate of 0.3 in the Maygen and Marine Scotland review is it moves upward to 37.2% or 0.37 in the SNH report. And again, another key debate, I suppose, was how much information to include about avoidance. It's been stated in the last session that we still really don't know very much about avoidance rates. And so in the Maygen report, they calculated collision rates based on a huge number of different avoidance rates, ranging from 50% all the way through to 99.5%. Meanwhile, Marine Scotland in 2013 suggested that actually we should include a 0% avoidance rate as well, because we just don't have enough information to make decisions. And again, the SNH report used various avoidance rates. So finally, if you go to the next slide, I'll just kind of bring that together in terms of the bottom line. So in the Maygen environmental statement, it was stated that about 1,000 grills and 911 adult salmon were expected to encounter a turbine, and that can be expressed as a percentage of the population. And what they noted was that depending on the avoidance rate, the population level effect decreased. So that those rates, for example, went down to 0.2% for adults when you applied a 50% avoidance rate. Meanwhile, just looking at the Marine Scotland and SNH review, they reflected the fact that the Maiden development was staged. So at present, there's only 4 turbines in the water, and they looked at 6 turbines. And they calculated that about 171 adult salmon were predicted to collide out of an adult population of 540,000 salmon. So, and in that, just to state that they assume no active avoidance. So 0.7 of all fish passing through a turbine were assumed to survive. But the interesting point is that they looked at an annual harvest of about 40,000 fish. So that's salmon that are harvested, and that only 13 salmon were lost from that annual harvest based on that modeling exercise. Next slide, please. But again, it's quite interesting to compare the Maygen environmental statement to the SNH guidance note that came out in 2016. And actually, on face value, looking at these 2 tables, both the table with no avoidance, so the top one, and the table assuming 95% avoidance, the bottom one, the numbers do look approximately similar, so they're within the same order of magnitude. However, it was noted in the SNH report that some of these differences mainly are could be attributed to the full frontal area of all 86 turbines being taken into account in the SNH report, and updated depth distributions, noting that less salmon were potentially within the turbine at-risk area. And also that modeling exercise incorporated a better reflection of how the turbine blades twisted, and that influenced the outcomes as well. So next slide, please. So just finally to say, what was the overall outcome? What happened? Well, in the Maygen environmental statement, no significant impact was identified for salmon. However, they agreed to undertake post-installation monitoring alongside Marine Scotland, and while no specific mitigation was identified, there is quite a lot of ongoing work happening around salmon migrating through the Pentland Firth. And I'm sure any colleagues from Marine Scotland who are in your breakout groups can tell you a lot more than I can about that. Next slide. So, and just finally to end, I just wanted to provide some references for those who are interested. All of that information is freely available online. So if you are really interested in collision modeling, I think it's a really interesting study of how using in the same area, doing a modeling exercise using different parameters can potentially change your inputs and outputs. So I think it's a really nice example. So that's all from me.
So when we talked about the pros and cons of the collision and encounter risk model, we noted that we do need to be pretty precise about the way we're using language, because it's not clear between the different kinds of models. We're really talking about different things. We probably aren't, but we need to get a lot clearer on those kinds of definitions and how we classify these. We saw some real pros for these models, particularly among the regulators and advisors, where there is the opportunity to really run the model many times with different avoidance rates, really get some plasticity to that model and get a range of what the outcomes might be. Allows you to use different parameter envelopes, levels of precaution, and so on, which is great. The problem, and therefore a con, is that this can give you a very wide sort of outcome, which tends to lead to precautionary approaches in consenting and licensing. But that there was really some value that if we looked at these models side by side and used them in this way, they could be very useful, with the caveat that, of course, they're only as good as the data that are going into them. And we recognize that a lot of the density data and other parameters going into the models aren't all that good. And that leads to the really big concern that if we race to models, we don't get good enough input parameters. These models are then taken as the truth, and they tend to sort of perpetuate some of these outcomes that may not be real. when we talked about what kind of field data we need to parameterize and validate the models, we talked about the need to have these much better density estimates using active acoustics, video where possible, but recognize some of the real downsides to video. But we spent a good deal of time here talking about how can we solve some of these collision risk model needs with well-placed research studies that really get at things like behavior, avoidance and evasion behavior, perhaps by groupings of fish, salmonids, gattids, etc. And if we had those, it would be exceptionally useful for regulators. There might still need to be some site-specific data collection, but it would really, really break down, decrease that amount of data needed. We also noted that as you begin to understand how the animals, how the fish react, what is their visual reaction to turbines, what is their reaction to the noise, you could also use this as a mitigation strategy. Could you sort of scare fish away from turbines with specific noises or specific visual signals? And then finally, we just had a chance to talk very briefly about how models might be used for assessing population level parameters, and everyone agreed if we had good collision or evasion encounter risk models going in, and we have fairly decent population models, they should be linked and you should get a pretty good outcome. And those population models, most people felt a good deal of confidence in for specific areas. And again, it comes down to the data you're putting in, how good those models are going to perform. That's kind of it in a nutshell. What did I miss, team? Okay, well, it's all on the Jamboards. So Jen, why don't you go ahead with the next one?
Yeah, thanks, Andrea. So we had some crossover with your discussion, which is really good. I think there was some consensus there with some of the things that your group was discussing. So I won't go over that. I'll just maybe pull out some of the other key things that we kind of focused on. So we definitely focused on, when you're talking about pros and cons of the different model types, there's pros in terms of their simplicity and ease of use, and lots of people being able to use them and understand them, but then there can be the con within that same vein of them being oversimplistic and having simple outcomes. We definitely talked about the need of really good solid information to feed the models in the first place, and where you don't have that great information, you're not going to get very good outcomes. And the same kind of goes for the validation of the models themselves as well. So we don't have a lot of validation around the assumptions and the parameters within the models. One thing we talked about quite a bit was how wonderful it would be, and I think your group talked about this as well, to be able to see the patterns coming from different sites and different species where similar models are being used, so that while we admit at the moment that we do need to do quite a lot of that data collection for site specific sites, in order to progress on this and improve on our data transferability, we need to be able to see where the patterns are emerging. And so there's maybe a little project in there, or a need for a group like OES Environmental to draw out where there are similar species being studied across the world, you know, maybe in Canada and in Scotland, and to be able to highlight that to researchers and to regulators so that it can be made the most of. You know, we can really take advantage of where those similar studies are being done, and those patterns may or may not be emerging. So that was a kind of a key point that we were focusing on. What else? I think those were kind of the key things. We did talk a little bit about population level effects then, and there was definitely an acknowledgement of the difficulty in being able to do that, and specifically in the consideration of how large some of the fish stocks or the populations might be that we're talking about in relation to, specifically to the smaller scale arrays that we're talking about. But even when we talk about scaling up to maybe, you know, 100 turbine arrays, if you're working with a huge stock or population of fish, it can be really, really difficult to get the fine scale data that you need to understand population level effects. I think those were kind of some of the key points. If anyone from my group wants to just pick out anything else, you're very welcome to, but I'll leave it there from me.
Thanks, Jan. Lisel, do you want to go ahead?
Yeah. So for us, we on the pro side for collision and counter risk model, it's the same as Hadi, as what Jen mentioned, that it is a very simple framework to follow, and there is a good structure, and you are able to build upon a model framework by putting in specific information and parameter. You can test a lot very quickly, and you can get also cautionary estimates for fish, and it can be used as illustrative and an analytical tool for communicating to developers and regulator. Some cons here is that, well, if you put, I like that, garbage in, garbage out, it's like whatever you are going to put in, it's going to be probably, you have to be aware of what you put in the model. And a lot of uncertainties on the inputs, which means that, as they are the same, like if you put uncertainties in the input, you are going to have uncertainty in the outputs of the model. And we have few like data to parameterize, and they are limited to certain device types. Also, we actually had Nicola on with us, and he did the simulation model. So is this model for the tidal kite, so it's a bit different. So what else we talked about? We talked about a bit of how do we use the field data? So talking about if we could have a way on a turbine to detect the collision, how would it be useful? And we had an engineer who was like, well, unless you have a huge fish, it's going to be complicated. But so we talk a bit about that, and the research project also with good instrumentation are needed, so help to extrapolate out, especially as moving towards array scale. So that's a good point. We mentioned for the site and turbine specific device type is something that is necessary, species behavior, breeding, habitat, etc. And finally, on population model, we actually, so the one I mentioned during this presentation is pretty much, yeah, what would be the worst case scenario for a population to crash, which is not really what is useful right now. And we talk about the possibility to combine collision risk model and population model. That's definitely useful. And we also, someone made a very good point, and we had talked about that before, so I'm glad someone talked about that, that for fish in the fishing industry as excellent population model, and we definitely should look more into that for fish. And if it's possible to scale observation on individual encounters to population and understand what mortality is, and does it make a difference at the end?
Great, thank you. Ran.
Great. I'll try and not repeat too much of what others have said, but in terms of the specific pros and cons of collision risk models, one of the interesting points that I thought came out for us was, as a pro, was that using a modeling approach for predicting environmental impacts has a good deal of precedence. So it's not necessarily an unusual thing. It's been done before, so potentially it can become more acceptable. We also thought, where it was mentioned that potentially encounter risk models could be easier to defend, given that they don't include the actual collision, although that brings in additional uncertainty as well. And I think one of the other groups mentioned that kind of leading to a more precautionary approach. And we also thought a good pro was the fact that models can be iterative, so they can be continually updated with more information. However, as others have mentioned, they're heavily dependent on assumptions and data that's not necessarily available. In terms of inputs for models, I think fish behavior, geometry of turbines has already been mentioned, but one key thing for us was that many species have site-specific behavior, and understanding the site specificity of particular behaviors is very important, and it's something that could make the transferability of collision modeling quite challenging. In terms of whether or not these can be used for populations, I suppose our answer is probably it would be nice, or maybe. And it was nice to hear the cell mention stock assessment, because that's something that we thought a bit about as well. But our perspective was that stock assessment models or fisheries models are very, very complex. So it's actually quite hard to imagine pulling that kind of information in to use collision risk models for a population. But perhaps most importantly, we need to define our population. So what does population mean? Is it community level? Is that community multiple species? Is it a single species? In terms of the example of salmon, a population is really considered to be a river level population. And the same thing with effects. So again, in that salmon case, the population level effects are those that come through to the next generation. So really thinking about actually maybe defining what we mean by population level effects a bit more. And I'll stop there.
Thanks, Rayanne. Lynette.
Yeah, so I'll try not to repeat the four before me. For the pros of the model, so the first thing that we talked about was that collision and encounter risk models are often presented together, and there is not one much better than the other for a regulatory point of view. And a pro is that it gives regulators a quantitative measure of impact. On the negative side, it gives also a number for developers to stick to. And it would give a bad image for them on the stakeholder, on the general public, societal side. Most of the cons that we discussed about were the data gap on all the data that these models need to run. Then let's move on to the input. So that we discussed a lot of actually the data gaps on what we need to know as input for parameterizing and validating the models. We need better understanding of the behavior of the fish before they encounter a turbine and after, on how they use the sites, on what the density of the fish, on the abundance, on all these kind of things. And also we briefly mentioned what are the best instruments to get those data. So that loops back to what we were discussing earlier in the first breakout group. And discussed about also the engineering side of the model. So what are the site-specific and turbine-specific characteristics that we need to know? For the sites, the depth, the tidal velocity, as a constraint, if it's a channel or open environment, these kind of things. And for a turbine, we mentioned the obvious rotational speed and tip speed, things like that, but also pressure field around the turbine blades, which is probably not something easy to measure. And for scaling up to population effect, what we discussed there was that it depends, it can be used, but it's very species specific, site specific, country specific. And we discussed a bit about the different species that are of interest or at risk for the different people that were in the group, on what is known or not known about the species, on the gap that we really need more field data about the different species and population characteristic of each species. And I will leave it there.
Great, thank you, Lynette. Catherine.
Okay, and last but not least, so our group discussed in terms of pros and cons. The model sensitivities has a pro and a con in the sense that, although you can see how your different variables impact your results, we kind of came to the conclusion that we don't have the evidence to properly define some of the input parameters. And another con that was brought out was that there's a lack of understanding in terms of the long-term consequences of collision and population effects. And yeah, the need to model over the lifetime of the development as well, that needs to be brought into consideration. In terms of the input data, we had a bit more kind of discussion around the site or turbine specific characteristics, looking at specific things such as turbine height of the bottom, blade length, rotor swept areas, as well as looking at tidal stage and considering the aggregation of fish at certain tidal states around high, low and slack tides. Considering not just the parameters for something such as a horizontal axis turbine, but considering vertical axis turbines and other novel developments. And one thing we were discussing about was looking at how much water goes through the turbine before the next potential impact as such. And that ties in with tidal flow rate. And should we be considering water clarity? There's an argument that the turbidity will affect the avoidance rate and diurnal behavior, but on the other side, fish have good senses before visual cues that need to be taken into account. And in terms of population level effects, well, the main thing that we discussed was, we need to define what the population is in the first instance and have an understanding of how different populations are using tidal channel. And considering in terms of the population definition, whether it's ecological or it's evolutionary context, and that some of the research now is leaning towards evolutionary context in that sense. And I think the last point is we need to consider the legal protection around populations as well. And I think that's most of the main points kind of run through from our group.
And these are the people you heard from today. Feel free to reach out to any of us at any time, or through TETHIS or through the ORJEP web page, and drop any thoughts you have, because we're always looking for the things that will make sense within the consenting community. So with that, I think we will end this workshop. Thank you.